I'm Jason Truluck, developer at SmartLogic, and I'm going to be talking about crawling and mining large data sets. So, just an overview of what I'm going to cover in my talk. I'm just going to talk a little bit about why you would want to do this, why you want to go ahead and look in big data sets, some of the challenges and the data sources that you can kind of leverage, and also how to extract the data and make it useful. So why? Data's everywhere. Have a whole bunch of data all around us. It's all over the place. It's what makes our applications really useful. Every industry is affected by it. So pretty much anything you can think of, whether it's sciences or finance or anything in the world, data plays a big part in what they do and how they can target and kind of leverage their audience. And some apps just have to have data to be interesting, like StarSpot. If there were no pictures of celebrities, that app would be very boring. So to give a little bit of a just kind of example of how large the world's data is, there's currently 3.2 zettabytes of data in the world right now. That's equivalent to about 3.2 billion terabytes or 3.2 trillion gigabytes, and that is a lot. In the next 6 years, it's estimated to grow to close to 40 zettabytes, and it's pretty much multiplying by 50 every single year. So that's pretty huge. Some possible data sources you can kind of get this data out of are APIs. We have things like Factual with locations and points of interest, Freebase, which is just a huge knowledge graph of pretty much everything. And of course, just common things like Twitter and Facebook for social media. There's also these kind of things in static data sets. Factual and Freebase both provide those, as well as Wikipedia. And data.gov is actually a really awesome data source. A lot of their data is not really that big, but there's a huge quantity of it and different types. And of course, the internet. So with APIs, there's some pros and cons to them. This is by no means exhaustive, but oftentimes they'll have the most recent information in whatever data set you're looking for, compared to a static data set that was compiled at some point in the past. They're very easy to consume. Some cons can be that they're, of course, slow, and there's rate limits. With static data sets, they're very easy to use locally, since you can just kind of download them if you have enough space, or just onto a large server or hard drive or something. They're very flexible in nature, so you can use a lot of different tools to kind of get the data out of it, even build your own, which can lead to some advancements in how we crawl data. Some cons are, of course, that they are very, very big. Most data sets don't fit locally on a computer unless you have some kind of external storage that you can put it on. And they can be of a pretty hard to consume format. So what I'm going to talk about further on in my talk is an RDF format. It's a resource description framework. And it's not anywhere near as consumable as something like JSON or XML. So the high-level process to kind of getting data out of APIs kind of works like this. I'm sure you guys have used it in the past, but you gather the data, determine its kind of current data structure, and then break that down into manageable chunks, pretty much divide and conquer, and then manipulate the data to get it to be what you want it to be. The example I'm going to cover is Freebase, particularly the films section of it. There's currently 2 billion odd facts in the entire Freebase graph. Around 2 million of them are film. And of course, about 50 million topics and 22 million of them being films. Facts are kind of the informational pieces, like a person's name. Topics are just things like a movie, an overarching object. And the benefit of this is that it's available as an API and a static data set. So as an API, it's all a graph structure, and they use a cool thing called the meta query language. It allows you to query the API similar to how you would a database, and sort of like RESTy. So it's a very familiar kind of structure. You basically can just build a JSON hash, send it off to their API, and they'll give you a JSON hash back. And the graph, of course, is just composed of just like nodes and edges, like any other graph, which gives it a very flexible schema. So they can pretty much add any kind of object back into the graph without having to like modify the structure beforehand. Some big challenges with it are the rate limiting, like I mentioned before. You can only make 100,000 requests a day and 10 requests per second. That seems like a lot, but when you get into actually like crawling this data source and you have millions and millions of data points you want to hit, it can take quite a long time to get through this limit. The speed, of course, like you're limited by how fast they're willing to return data to you and how fast your network is. A lot of times you can kind of like mitigate this by requesting things in smaller chunks, but then that goes and ends up eating into your API request limit. Also, like not repeating previous queries. You want to be as efficient as possible, of course, so you're not wasting those request limits. Timeouts and just missing keys, since it is a node-based graph, or a graph-based data structure. There's a lot of times where you can just not assume that something is going to exist on an object. And a lot of times, if you expect it to exist and don't specify how you want to crawl it like in that way, it will just return nothing for all of the things you requested, which in my opinion is a little bit of a downside to it, but that's particular to this API. So, yeah.
So, presumably, whoever creates the database and manages the database has to set up indices?
Well, that's actually one of the good parts about it is it's not really managed at all. It's completely freeform. So since it's like just a graph, you can inject a new data structure or anything into the graph at any point. So I'm sure they like index the data in some way. I'm not entirely sure how, but there's no like one manager that controls like specifying like in Postgres like you index on this column. There is no like column technically, so it's kind of like foreign in that way. But moving on, just like how would you kind of like break this down? So first of all, you'd want to like determine what kind of like schema your data is going to have. That's kind of the first point that I talked about in the general section of determining the structure. And I just usually put that in the just like crawl schemas directory of my app, and then build like a queuing worker. This is basically going to be used to divide up the different sections of the API you're going to be crawling and kind of like building those queues. Then a crawling worker orchestrated by the queuing worker. The queuing worker kind of manages like sending out all of these like workers to go grab the actual requests. And the crawlers are what actually like send the request to grab it out of the API. Then you have something that's like a master importer worker. This will help set up just recurrence and also specify how we want to manipulate our data to get it back into our system and how we want it. So in a way, this is kind of like manipulating this graph to be into a relational database in my case. Yeah.
So what you're talking about now is something that consumes an API?
Yeah. So this will be like how you can crawl the API, get it into your system, and then kind of like make it relative to what you want to use. So like it takes all that data in the format it's in and then pushes it into whatever structure you want, like a relational database that you can then index and use for your app. So crawl schemas, as I kind of gleaned over, they identify the structure of the current data. It's supplied by a JSON file and sent off to the API request. One of the really good benefits is it gives a clear representation of what data will be gathered from that request. I have a little example here. That is not... So this is a pretty like trivial example, but this is what you would use to like get a request to like the film API endpoint on the Freebase API. This is just specifying that I want the MID back from it, the GUID. Both of these are unique identifiers in the Freebase system to kind of like call back to this object in the future. The name of the movie, its release date, and this specifies the type of object I'm requesting and the limit that I want. So I'm saying, give me all of this information for a film, times 1,000. So it'll get 1,000 films on this API request. And this is kind of one of the hard parts, is like building a limit that is actually consumable before the timeout. Because if you specify all million of them, you're not going to be able to complete that request in time, and it'll time out after 30 seconds.
That's standard MQL format?
Well, this is just the JSON that they use to process, or the MQL uses to process your query. So this is one way that they have to do it. In my opinion, it was the easiest way. But yeah, in a sense.
But you couldn't pass a YAML file unless they explicitly supported that?
I don't think they support YAML, no. It's strictly JSON, I think.
Being the fill-in or the provider of the API?
Yeah. Okay. So the next thing we have on the list is the queuer. So as I said before, this kind of like orchestrates the crawling jobs for each of the domains of data. The domains being like films, actors, directors, those kind of things. And it handles the recurrence for continued crawling in the future. So obviously, there's new films coming out all the time. We can't just say we're going to do this once and then give it up. Every week, we should kind of like crawl this and get more new data that came out. And just an example of one of these, I'll kind of go through this pretty quickly. But we have here the recurrence, like I mentioned. This is just saying like do this every 3 days. Then it has a perform method, which goes through each of our crawl areas. These would be the schema files, like the JSON files that we have, and pushes it onto one of the crawlers that we're going to go over next. And then basically, that's all this does. It's very simple, just kind of like keeps it on track and creates the like workers that are eventually going to get the data for us. So then we have the crawler. This is responsible, like I said, for building the queries, gathering the data, and storing it for later processing. I'm actually just going to stay out of this for the future. This is also kind of just like a simple example here. We have here where it's just saying like the type that's getting is a film. The cursor is kind of like the referential point in the big set of films that the API gives back to you. So this is how you know in future requests like what set you or what page you're on, and how you can like kind of like scoot through that. And this is dynamically generated on each API request or each like set that you've queried against. So it's unique to your current like cycle. So then we go through like while there is a cursor, we continue crawling and queuing more workers. Then this call is just like a splitting file. The crawl here this is just basically specifying the crawl query, which is the JSON we had before, the cursor, our API key, so that we're validated, and then says, hey, go ahead and grab that data from the endpoint. These are just some helper methods just to export the data that we've grabbed to a file so we can save that for later use. And kind of like put that off for later processing if we wanted to. Then we have the importers. There's one kind of like main orchestrator. This is a very similar thing to what the queuing worker does. It basically just gets all of the different areas that we've crawled, like I said before, like film, actors, and stuff like that. Since all of the different files are broken down by their type in the structure I've made, and then just goes ahead and queues one of the import workers for that particular type to import that data. So this kind of like matches the data that we've crawled to the structure that we want it to be, and then the importer that gets queued from this actually pulls that data in. And this is an example of one of those just importers. This is just for the film that we had before. So you'll get a list of JSON data. It'll have different things. This is how we manipulate the date to get it into the format that we want. Checking to see if this already exists in the database. So we'll just update it or skip it, depending on what we want to do. If it already exists, based on the unique IDs we've grabbed before and the name. And and then basically just save the instance of whatever object that is and that we've gone through. So the results of this, the initial import took about like 12 days of constant running. This was all just on my local machine. Imported about 4 million unique entities from it, that including like films, actors, genres, all that kind of different stuff. So it wasn't too bad. It's just, it takes a lot of time. I guess it's not really like that much to wait, because it's just workers kind of like going away at them.
It's all coming from one IP address.
Yeah, I mean, there's many ways I could have like expedited that by like just putting it up on a server or like striping it across that and doing that, but I didn't want to pay for it. So the next kind of thing that we have is a data dump. Like I mentioned before, Freebase comes in this flavor as well. It's about 28 gigs compressed and 280 gigs uncompressed. So it's too large to fit on my laptop when I uncompress it, so I can't actually do it in that way. It's stored in a gzipped RDF format, and it's just using n-triples. The n-triples is just kind of like the description or the line-based separator or serialization format that RDF uses. And using commands like zgrep and cut, I was able to kind of like get the data out of this pretty quickly without having to decompress it. So I can just read the compressed file and use the scripting language, in this case Ruby, to parse the data out.
Question?
Yeah.
We get into processing the data. So the way you imported it, is that a standard pattern? Or
I should have predicated my talk. This is, I think it's common. I don't think it's like known or like a set standard. I'm sure this is very naive in like how to implement it, but I think like, yeah, one of many. But divide and conquer is a pretty common pattern. Okay, so going from that, we're back to the command line. So now that we have this like 22 or 28 gigabyte file, which is manageable on my local machine, I can go ahead and just offload to the command line. It's fast by comparison to the API. It takes roughly about like 10 to 20 minutes, depending on how much other stuff I'm doing on my computer, to go through this entire compressed file and search for the things that I want. It needs a lot more massaging to get the data correct. So I'll give an example of what kind of like it's outputted by this in a few more slides up. And you'll see that it's like not nearly as nice as an API response. You don't get nice JSON back at all. And the basic steps are just to use zgrep, which is very similar to grep, but it just allows you to grep compressed files, or gzip files specifically, for the content you want, and then save that out to a text file. And then we're going to feed that output into workers to extract that data from the text file, very similar to the API. So an example of this is just this command right here. This is basically saying like grep this file, the Freebase latest gzipped file for things in the film domain of a type instance. And an instance is basically what it sounds like. It's an instance of this type. So like Iron Man would be an example of that. Then pipe this into cut, which will give us the actual like sections of the data we want. Pipe it into cut again, and that'll grab out these MIDs. And then we'll basically just use these MIDs that we've saved to go back through the data set and get each individual item we want. So more of this stuff. Like I said, we're going to use the MIDs, just go through, cut out the data we want, and then pull this data in columns and save it. This is the way we get the things like actors and genres and descriptions. And that brings me to the command I was running before. This is an example. This is running on the current dump of the Freebase information. As you can see, this is not very pretty, but it basically gives you this.
Make it a little bit better.
Yeah. This is the MID we're searching for right here. As you can see, it's just like grepping through the file for that MID. And these are the different like matching objects that came up for that. Each of these lines is one of the like facts in the database or in the data. So for example, we have things, let's see if I can find one. We'll go to this. Is just like a kind of like parse out example I had. This is an example of the movie 45. I'm not really sure what it is, but it came up first. It is the description. So you get something like freebase NS common type topic description, and that's the data right there for what the description of the movie is. And this is an example of like an output file that we would then throw to the workers to process. And you can get things like relations, like genres, actors starring in it, and language. So as I mentioned, you can just throw this into more workers. Go ahead and show an example of that. This is a very naive approach to this as well. These are some like parse rules that I've set up. Basically, it's saying like if you come across this different key in the data as we're like matching for it, we want to capture that. If it's a genre, we want to crawl again because we only have the like relation to that data, so we need to actually go get it again. Then it pushes it through this worker, saying for each of the parse rules, if the item matches that key, process the line with that parse rule. Capture being, like I said, grab the data out of that matched set. In most cases, it's going to be in quotes. This, of course, probably needs to be a little bit more robust. If not, call this again to crawl the data for the relation that we have.
Does this work?
It does, not very well.
Typo on line 28?
Probably. I tried it really quickly, like 4 nights ago, so it kind of worked.
Looks like a typo.
It probably is. I probably didn't come across that line. I don't know. But the results of that, just kind of like some estimations. I haven't run it through the entire thing, but an import could take about 3 days on a 4-core computer. Since zgrep is single-threaded, you can't like thread it across multiple things. You have to run separate instances of it. So in my case, be 4 cores. Other options for it, you could use like Hadoop and MapReduce. It can process a lot of information very, very quickly since you can just build a giant cluster of servers and push all this data onto it and go through it really, really fast. But it's very expensive. The common way is to spool up like the largest instance on any kind of like cloud computing service and then push on the data to it. And for 100 4x large instances on Amazon would be almost 10 grand. I don't have that kind of money, so I didn't do it. And some other things that I could use is like a more appropriate language to parse this data, like Java, Python, or Go. Ruby is obviously not the fastest candidate, but it's what I know. So. And some useful links. There's some different things, YouTube video that Google actually put up to use their compute engine to process things with Hadoop and MapReduce. Just like some things of why data matters. And there's currently a Coursera course that just came out about mining massive data sets, if anybody's interested in learning more.